Air conditioning.
Air conditioning is the process of altering the properties of air to more favorable conditions, typically with the aim of distributing the conditioned air to an occupied space to improve comfort. More generally, air conditioning can refer to any form of technology, heating, cooling, dehumidification, humidification, cleaning, ventilation, or air movement, that modifies the condition of air. An air conditioner is a major or home appliance, system, or mechanism designed to change the air temperature and humidity within an area, used for cooling and sometimes heating depending on the air properties at a given time. The cooling is typically done using a simple refrigeration cycle, but sometimes evaporation is used, commonly for comfort cooling in buildings and motor vehicles. In construction, a complete system of heating, ventilation and air conditioning is referred to as HVAC. Air conditioning can also be provided by a simple process called free cooling, which uses pumps to circulate a coolant, typically water or a glycol mix, from a cold source, which in turn acts as a heat sink for the energy that is removed from the cooled space. Free cooling systems can have very high efficiencies, and are sometimes combined with seasonal thermal energy storage, STES, so the cold of winter can be used for summer air conditioning. Common storage media are deep aquifers or a natural underground rock mass accessed via a cluster of small diameter, heat exchanger-equipped boreholes. Some systems with small storage are hybrids, using free cooling early in the cooling season, and later employing a heat pump to chill the circulation coming from the storage. The heat pump is added in because the temperature of the storage gradually increases during the cooling season, thereby declining in effectiveness. Free cooling and hybrid systems are mature technology.
History.
The basic concept behind air conditioning is said to have been applied in ancient Egypt, where reeds were hung in windows and were moistened with trickling water. The evaporation of water cooled the air blowing through the window, though this process also made the air more humid, also beneficial in a dry desert climate. In ancient Rome, water from aqueducts was circulated through the walls of certain houses to cool them. Other techniques in medieval Persia involved the use of cisterns and wind towers to cool buildings during the hot season. Modern air conditioning emerged from advances in chemistry during the 19th century, and the first large-scale electrical air conditioning was invented and used in 1902 by Willis Carrier. The introduction of residential air conditioning in the 1920s helped enable the Great Migration to the Sun Belt in the U.S. St George's Hall in Liverpool, England, built between 1841 and 1854, was, in 2005, awarded a blue plaque by the Heritage Group of the CIBSE recognizing it as the world's first air-conditioned building.
Mechanical cooling.
The 2nd century Chinese inventor Ding Huan, Thor 180, of the Han Dynasty invented a rotary fan for air conditioning, with 7 wheels 3m, 9.8 feet, in diameter and manually powered. In 747, Emperor Xuanzong, r. 712–762, of the Tang Dynasty, 618–907, had the Cool Hall, Liang Tian, built in the Imperial Palace, which the Tang Yulin describes as having water-powered fan wheels for air conditioning as well as rising jet streams of water from fountains. During the subsequent Song Dynasty, 960–1279, written sources mentioned the air conditioning rotary fan as even more widely used. In the 17th century, Cornelis Drebbel demonstrated turning summer into winter for James I of England by adding salt to water. In 1758, Benjamin Franklin and John Hadley, a chemistry professor at Cambridge University, conducted an experiment to explore the principle of evaporation as a means to rapidly cool an object. Franklin and Hadley confirmed that evaporation of highly volatile liquids such as alcohol and ether could be used to drive down the temperature of an object past the freezing point of water. They conducted their experiment with the bulb of a mercury thermometer as their object and with the bellows used to quicken the evaporation. They lowered the temperature of the thermometer bulb down to 14 degC, 7 degF, while the ambient temperature was 18 degC, 64 degF. Franklin noted that, Soon after they passed the freezing point of water 0 degc, 32 degf, a thin film of ice formed on the surface of the thermometer's bulb and that the ice mass was about a quarter-inch thick when they stopped the experiment upon reaching 14 degc, 7 degf. Franklin concluded, "From this experiment one may see the possibility of freezing a man to death on a warm summer's day." In 1820, English scientist and inventor Michael Faraday discovered that compressing and liquefying ammonia could chill air when the liquefied ammonia was allowed to evaporate. In 1842, Florida physician John Gorrie used compressor technology to create ice, which he used to cool air for his patients in his hospital in Apalachicola, Florida. He hoped eventually to use his ice-making machine to regulate the temperature of buildings. He even envisioned centralized air conditioning that could cool entire cities. Though his prototype leaked and performed irregularly, Gorrie was granted a patent in 1851 for his ice-making machine. His hopes for its success vanished soon afterwards when his chief financial backer died. Gorrie did not get the money he needed to develop the machine. According to his biographer, Vivian M. Sherlock, he blamed the Ice King, Frederick Tudor, for his failure, suspecting that Tudor had launched a smear campaign against his invention. Dr. Gorrie died impoverished in 1855, and the idea of air conditioning faded away for 50 years. Since prehistoric times, snow and ice were used for cooling. The business of harvesting ice during winter and storing for use in summer became popular towards the late 19th century. This practice was replaced by mechanical ice-making machine. James Harrison's first mechanical ice-making machine began operation in 1851 on the banks of the Barwon River at Rocky Point in Geelong, Australia. His first commercial ice-making machine followed in 1854, and his patent for an ether vapor compression refrigeration system was granted in 1855. This novel system used a compressor to force the refrigeration gas to pass through a condenser, where it cooled down and liquefied. The liquefied gas then circulated through the refrigeration coils and vaporized again, cooling down the surrounding system. The machine employed a 5M, 16 feet flywheel and produced 3,000 kilograms, 6,600 pounds, of ice per day. Though Harrison had commercial success establishing a second ice company back in Sydney in 1860, he later entered the debate over how to compete against the American advantage of unrefrigerated beef sales to the United Kingdom. He wrote fresh meat frozen and packed as if for a voyage, so that the refrigerating process may be continued for any required period, and in 1873 prepared the sailing ship Norfolk for an experimental beef shipment to the United Kingdom. His choice of a cold room system instead of installing a refrigeration system upon the ship itself proved disastrous when the ice was consumed faster than expected.
Electromechanical cooling.
In 1902, the first modern electrical air conditioning unit was invented by Willis Carrier in Buffalo, New York. After graduating from Cornell University, Carrier, a native of Angola, New York, found a job at the Buffalo Forge Company. While there, Carrier began experimenting with air conditioning as a way to solve an application problem for the Sackett-Wilhelms Lithographing and Publishing Company in Brooklyn, New York, and the first air conditioner, designed and built in Buffalo by Carrier, began working on July 17, 1902. Designed to improve manufacturing process control in a printing plant, Carrier's invention controlled not only temperature but also humidity. Carrier used his knowledge of the heating of objects with steam and reversed the process. Instead of sending air through hot coils, he sent it through cold coils, ones filled with cold water. The air blowing over the cold coils cooled the air, and one could thereby control the amount of moisture the colder air could hold. In turn, the humidity in the room could be controlled. The low heat and humidity helped maintain consistent paper dimensions and ink alignment. Later, Carrier's technology was applied to increase productivity in the workplace, and the Carrier Air Conditioning Company of America was formed to meet rising demand. Over time, air conditioning came to be used to improve comfort in homes and automobiles as well. Residential sales expanded dramatically in the 1950s. In 1906, Stuart W. Cramer of Charlotte, North Carolina was exploring ways to add moisture to the air in his textile mill. Cramer coined the term air conditioning, using it in a patent claim he filed that year as an analog to water conditioning, then a well-known process for making textiles easier to process. He combined moisture with ventilation to condition, and changed the air in the factories, controlling the humidity so necessary in textile plants. Willis Carrier adopted the term and incorporated it into the name of his company. The evaporation of water in air, to provide a cooling effect, is now known as evaporative cooling. Evaporative cooling was the first real air conditioning and shortly thereafter the first private home to have air conditioning. The Dubose House was built in Chapel Hill, North Carolina in 1933. Realizing that air conditioning would one day be a standard feature of private homes, particularly in the South, David Street Pierre Dubose, 1898–1994, designed an ingenious network of ductwork and vents, all painstakingly disguised behind intricate and attractive Georgian-style open moldings. Meadowmont is believed to be one of the first private homes in the United States equipped for central air conditioning. In 1945, Robert Sherman of Lynn, Massachusetts, invented the portable, in-window air conditioner that cooled and heated, humidified and dehumidified, and filtered the air, patent 2,433,960 granted January 6, 1948. It was subsequently stolen by a large manufacturer. Sherman did not have the resources to fight the big corporation in court, they promised to break him if he tried, and thus never received any money or recognition. He died in 1962. Patent at http://navlog.org/ patent_1.html.
Refrigerant development.
The first air conditioners and refrigerators employed toxic or flammable gases, such as ammonia, methyl chloride, or propane, that could result in fatal accidents when they leaked. Thomas Midgley, Jr. created the first non-flammable, non-toxic chlorofluorocarbon gas, Freon, in 1928. Freon is a trademark name owned by DuPont for any chlorofluorocarbon, CFC, hydrochlorofluorocarbon, HCFC, or hydrofluorocarbon, HFC, refrigerant, the name of each including a number indicating molecular composition, R11, R12, R22, R134A. The blend most used in direct expansion home and building comfort cooling is an HCFC known as R22. It was to be phased out for use in new equipment by 2010, and is to be completely discontinued by 2020. R12 was the most common blend used in automobiles in the U.S. until 1994, when most designs changed to a 134A. R11 and R12 are no longer manufactured in the U.S. for this type of application, the only source for air conditioning repair purposes being the cleaned and purified gas recovered from other air conditioner systems. Several non-ozone depleting refrigerants have been developed as alternatives, including R410A, invented by Allied Signal, now part of Honeywell, in Buffalo, and sold under the Gentron, AZ20 name. It was first commercially used by Carrier under the brand name Puron. Innovation in air conditioning technologies continues, with much recent emphasis placed on energy efficiency and on improving indoor air quality. Reducing climate change impact is an important area of innovation because, in addition to greenhouse gas emissions associated with energy use, CFCs, HCFCs, and HFCs are, themselves, potent greenhouse gases when leaked to the atmosphere. For example, R22, also known as HCFC22, has a global warming potential about 1,800 times higher than CO2. As an alternative to conventional refrigerants, natural alternatives, such as carbon dioxide, CO2, R744, have been proposed.
Refrigeration cycle.
In the refrigeration cycle, a heat pump transfers heat from a lower temperature heat source into a higher temperature heat sink. Heat would naturally flow in the opposite direction. This is the most common type of air conditioning. A refrigerator works in much the same way. as it pumps the heat out of the interior and into the room in which it stands. This cycle takes advantage of the way phase changes work, where latent heat is released at a constant temperature during a liquid-gas phase change, and where varying the pressure of a pure substance also varies its condensation boiling point. The most common refrigeration cycle uses an electric motor to drive a compressor. In an automobile, the compressor is driven by a belt over a pulley, the belt being driven by the engine's crankshaft, similar to the driving of the pulleys for the alternator, power steering, etc. Whether in a car or building, both use electric fan motors for air circulation. Since evaporation occurs when heat is absorbed, and condensation occurs when heat is released, air conditioners use a compressor to cause pressure changes between two compartments, and actively condense and pump a refrigerant around. A refrigerant is pumped into the evaporator coil, located in the compartment to be cooled, where the low pressure causes the refrigerant to evaporate into a vapor, taking heat with it. At the opposite side of the cycle is the condenser, which is located outside of the cooled compartment, where the refrigerant vapor is compressed and forced through another heat exchange coil, condensing the refrigerant into a liquid, thus releasing the heat previously absorbed from the cooled space. By placing the condenser, where the heat is rejected, inside a compartment, and the evaporator, which absorbs heat, in the ambient environment, such as outside, or merely running a normal air conditioner's refrigerant in the opposite direction, the overall effect is the opposite, and the compartment is heated. This is usually called a heat pump, and is capable of heating a home to comfortable temperatures, 25 degC, 77 degF, even when the outside air is below the freezing point of water, 0 degC, 32 degF. Cylinder unloaders are a method of load control used mainly in commercial air conditioning systems. On a semi-hermetic, or open, compressor, the heads can be fitted with unloaders which remove a portion of the load from the compressor so that it can run better when full cooling is not needed. Unloaders can be electrical or mechanical.
Humidity control.
Refrigeration air conditioning equipment usually reduces the absolute humidity of the air processed by the system. The relatively cold, below the dew point, evaporator coil condenses water vapor from the processed air, much like an ice-cold drink will condense water on the outside of a glass, sending the water to a drain and removing water vapor from the cooled space and lowering the relative humidity in the room. Since humans perspire to provide natural cooling by the evaporation of perspiration from the skin, drier air, up to a point, improves the comfort provided. The comfort air conditioner is designed to create a 40% to 60% relative humidity in the occupied space. In food retailing establishments, large open chiller cabinets act as highly effective air dehumidifying units. A specific type of air conditioner that is used only for dehumidifying is called a dehumidifier. A dehumidifier is different from a regular air conditioner in that both the evaporator and condenser coils are placed in the same air path, and the entire unit is placed in the environment that is intended to be conditioned, in this case dehumidified, rather than requiring the condenser coil to be outdoors. Having the condenser coil in the same air path as the evaporator coil produces warm, dehumidified air. The evaporator, cold, coil is placed first in the air path, dehumidifying the air exactly as a regular air conditioner does. The air next passes over the condenser coil, rewarming the now dehumidified air. Having the condenser coil in the main air path rather than in a separate, outdoor air path, as with a regular air conditioner, results in two consequences: the output air is warm rather than cold, and the unit is able to be placed anywhere in the environment to be conditioned, without a need to have the condenser outdoors. Unlike a regular air conditioner, a dehumidifier will actually heat a room just as an electric heater that draws the same amount of power, watts, as the dehumidifier would. A regular air conditioner transfers energy out of the room by means of the condenser coil, which is outside the room, outdoors. That is, the room can be considered a thermodynamic system from which energy is transferred to the external environment. Conversely, with a dehumidifier, no energy is transferred out of the thermodynamic system, room, because the air conditioning unit, dehumidifier, is entirely inside the room. Therefore all of the power consumed by the dehumidifier is energy that is input into the thermodynamic system, the room, and remains in the room, as heat. In addition, if the condensed water has been removed from the room, the amount of heat needed to boil that water has been added to the room. This is the inverse of adding water to the room with an evaporative cooler. Dehumidifiers are commonly used in cold, damp climates to prevent mold growth indoors, especially in basements. They are also used to protect sensitive equipment from the adverse effects of excessive humidity in tropical countries. The engineering of physical and thermodynamic properties of gas-vapor mixtures is called psychrometrics.
Energy.
In a thermodynamically closed system, any power dissipated into the system that is being maintained at a set temperature, which is a standard mode of operation for modern air conditioners, requires that the rate of energy removal by the air conditioner increase. This increase has the effect that, for each unit of energy inputs into the system, say to power a light bulb in the closed system, the air conditioner removes that energy. In order to do so, the air conditioner must increase its power consumption by the inverse of its efficiency, coefficient of performance, times the amount of power dissipated into the system. As an example, assume that inside the closed system a 100 W heating element is activated, and the air conditioner has an coefficient of performance of 200%. The air conditioner's power consumption will increase by 50 W to compensate for this, thus making the 100 W heating element cost a total of 150 W of power. It is typical for air conditioners to operate at efficiencies of significantly greater than 100%. However, it may be noted that the input's electrical energy is of higher thermodynamic quality, lower entropy, than the output thermal energy, heat energy. Air conditioner equipment power in the U.S. is often described in terms of tons of refrigeration. A ton of refrigeration is approximately equal to the cooling power of 1 short ton, 2,000 pounds or 907 kilograms, of ice melting in a 24-hour period. The value is defined as 12,000 British thermal units per hour, or 3517 watts. Residential central air systems are usually from 1 to 5 tons, 3 to 20 kilowatts, kilowatt in capacity. In an automobile, the AC system will use around 4 horsepower, 3 kilowatts, of the engine's power.
Seasonal energy efficiency ratio.
For residential homes, some countries set minimum requirements for energy efficiency. In the United States, the efficiency of air conditioners is often, but not always, rated by the Seasonal Energy Efficiency Ratio, SEER. The higher the SEER rating, the more energy efficient is the air conditioner. The SEER rating is the British thermal unit of cooling output during its normal annual usage divided by the total electric energy inputs in watt-hours, WH, during the same period. This can also be rewritten as, for example, a 5,000 British thermal units per hour air conditioning unit, with a SEER of 10, would consume 5,000 tenths equals 500 watts of power on average. The electrical energy consumed per year can be calculated as the average power multiplied by the annual operating time. Assuming 1,000 hours of operation during a typical cooling season, that is, 8 hours per day for 125 days per year. Another method that yields the same result, is to calculate the total annual cooling output. Then, for a SEER of 10, the annual electrical energy usage would be. SEER is related to the coefficient of performance, COP, commonly used in thermodynamics and also to the energy efficiency ratio, EER. The EER is the efficiency rating for the equipment at a particular pair of external and internal temperatures, while SEER is calculated over a whole range of external temperatures, that is, the temperature distribution for the geographical location of the SEER test. SEER is unusual in that it is composed of an imperial unit divided by an SI unit. The COP is a ratio with the same metric units of energy, joules, in both the numerator and denominator. They cancel out, leaving a dimensionless quantity. Formulas for the approximate conversion between SEER and EER or COP are available from the Pacific Gas and Electric Company. From equation 2, above, a CR of 13 is equivalent to a COP of 3.43, which means that 3.43 units of heat energy are pumped per unit of work energy. The United States now requires that residential systems manufactured in 2006 have a minimum CR rating of 13, although window box systems are exempt from this law, so their CR is still around 10.
Design. Types. Window and through-wall.
Room air conditioners come in two forms: unitary and packaged terminal (PTAC) systems. Unitary systems, the common one-room air conditioners, sit in a window or wall opening, with interior controls. Interior air is cooled as a fan blows it over the evaporator. On the exterior the air is heated as a second fan blows it over the condenser. In this process, heat is drawn from the room and discharged to the environment. A large house or building may have several such units, permitting each room to be cooled separately. PTAC systems are also known as wall-split air conditioning systems or ductless systems. These PTAC systems, which are frequently used in hotels, have two separate units, terminal packages, the evaporative unit on the interior and the condensing unit on the exterior, with tubing passing through the wall and connecting them. This minimizes the interior system footprint and allows each room to be adjusted independently. PTAC systems may be adapted to provide heating in cold weather either directly by using an electric strip, gas or other heater, or by reversing the refrigerant flow to heat the interior and draw heat from the exterior air, converting the air conditioner into a heat pump. While room air conditioning provides maximum flexibility, when used to cool many rooms at a time it is generally more expensive than central air conditioning. The first practical through-the-wall air conditioning unit was invented by engineers at Chrysler Motors and offered for sale starting in 1935.
Split systems.
Split-system air conditioners come in two forms, central and mini-split. In both types, the inside environment, evaporative, heat exchanger and fan is separated by some distance from the outside environment, condensing unit, heat exchanger and fan. In central air conditioning, the inside heat exchanger is typically placed inside the central furnace AC unit of forced air heating system, which is then used in the summer to distribute chilled air throughout a residence or commercial building. A mini-split system typically supplied chilled air to only a single space, and thus was sometimes referred to as split-system single-zone air conditioning. Today, however, one split-system compressor can supply chilled air to up to 8 indoor units. If the split system contains a heat pump, as is often the case, the system may be easily switched seasonally to supply heat instead of cold. Controls can be wall-mounted or handheld, the size of the remote control for a television.
Ductless split system air conditioning.
Mini-split systems, today usually called ductless air conditioners, typically produce 9,000 to 36,000 British thermal units, 9,500 to 38,000 kilojoules, per hour of cooling. Most ductless systems are similar to PTAC air conditioners in that they are often designed to cool a single room or space, but ductless air conditioning allows design and installation flexibility because the inside wall space required is significantly reduced and the compressor and heat exchanger can be located further away from the inside space, rather than merely on the other side of the same unit as in a PTAC or window air conditioner. In addition, ductless systems will offer much higher efficiency, up to 27.1 SEER on some systems. Today's brands include Aircon, Carrier, Daikin, Climair, LG, Mitsubishi, Sanyo, Fujitsu and YMGI. Most ductless, split-system, air conditioners still typically provide cooling to a single room or interior zone, just like a window air conditioner or PTAC. But more powerful outside units are becoming more and more available, supporting cooling of ever more interior zones. Advantages of the ductless system include smaller size and flexibility for zoning or heating and cooling individual rooms. Flexible exterior hoses lead from the outside unit to the interior one. These are often enclosed with metal to look like common drain pipes from the roof. Those enclosures can be painted to match the color of the house. The primary disadvantage of ductless air conditioners is their cost. Such systems cost about $1,500 to $2,000 per ton, 12,000 British thermal units per hour, of cooling capacity. This is about 30% more than central systems, not including ductwork, and may cost more than twice as much as window units of similar capacity. An additional possible disadvantage that may increase net cost is that ductless systems may sometimes not be eligible for energy efficiency rebates offered by many electric utility companies as part of an incentive program to reduce summer cooling load on the electrical grid.
Central air conditioning.
Central, ducted, air conditioning offers whole house or large commercial space cooling, and often offers moderate multi-zone temperature control capability by the addition of air louver control boxes.
Evaporative coolers.
In very dry climates, evaporative coolers, sometimes referred to as swamp coolers or desert coolers, are popular for improving coolness during hot weather. An evaporative cooler is a device that draws outside air through a wet pad, such as a large sponge soaked with water. The sensible heat of the incoming air, as measured by a dry bulb thermometer, is reduced. The total heat, sensible heat plus latent heat, of the entering air is unchanged. Some of the sensible heat of the entering air is converted to latent heat by the evaporation of water in the wet cooler pads. If the entering air is dry enough, the results can be quite cooling. Evaporative coolers tend to feel as if they are not working during times of high humidity, when there is not much dry air with which the coolers can work to make the air as cool as possible for dwelling occupants. Unlike other types of air conditioners, evaporative coolers rely on the outside air to be channeled through cooler pads that cool the air before it reaches the inside of a house through its air duct system. This cooled outside air must be allowed to push the warmer air within the house out through an exhaust opening such as an open door or window. These coolers cost less and are mechanically simple to understand and maintain. An early type of cooler, using ice for a further effect, was patented by John Gorrie of Apalachicola, Florida in 1842. He used the device to cool the patients in his malaria hospital.
Portable units.
A portable air conditioner is one on wheels that can be easily transported inside a home or office. They are currently available with capacities of about 5,000 to 60,000 British thermal units per hour, 1,800 to 18,000 W output, and with and without electric resistance heaters. Portable air conditioners are either evaporative or refrigerative. Portable refrigerative air conditioners come in two forms, split and hose. These compressor-based refrigerant systems are air-cooled, meaning they use air to exchange heat, in the same way as a car or typical household air conditioner does. Such a system dehumidifies the air as it cools it. It collects water condensed from the cooled air and produces hot air which must be vented outside the cooled area. Doing so transfers heat from the air in the cooled area to the outside air. A portable split system has an indoor unit on wheels connected to an outdoor unit via flexible pipes, similar to a permanently fixed installed unit. Hose systems, which can be monoblock or air-to-air, are vented to the outside via air ducts. The monoblock type collects the water in a bucket or tray and stops when full. The air-to-air type re-evaporates the water and discharges it through the ducted hose and can run continuously. A single duct unit uses air from within the room to cool its condenser, and then vents it outside. This air is replaced by hot air from outside or other rooms, thus reducing the unit's effectiveness. Modern units might have a coefficient of performance, COP, sometimes called efficiency of approximately 3, that is, 1 kilowatt of electricity will produce 3 kilowatts of cooling. A dual-duct unit draws air to cool its condenser from outside instead of from inside the room, and thus is more effective than most single-duct units. Evaporative air coolers, sometimes called swamp coolers, do not have a compressor or condenser. Liquid water is evaporated on the cooling fins, releasing the vapor into the cooled area. Evaporating water absorbs a significant amount of heat, the latent heat of vaporization, cooling the air, Humans and animals use the same mechanism to cool themselves by sweating. They have the advantage of needing no hoses to vent heat outside the cooled area, making them truly portable. And they are very cheap to install and use less energy than refrigerative air conditioners. Disadvantages are that unless ambient humidity is low, as in a dry climate, cooling is limited and the cooled air is very humid and can feel clammy. Also, they use a lot of water, which is often at a premium in the dry climates where they work best. A typical single-hosed portable air conditioner can cool a room that is 475 square feet, 44.1 m2, or smaller and has at most a cooling power of 15,000 BTUs-H, 4.3 kilowatts. However, single-hosed units cool a room less effectively than dual-hosed as the air expelled from the room through the single hose creates negative pressure inside the room. Because of this, air, potentially warm air, from neighboring rooms is pulled into the room with the cooling unit to compensate.
Heat pumps.
Heat pump is a term for a type of air conditioner in which the refrigeration cycle can be reversed, producing heating instead of cooling in the indoor environment. They are also commonly referred to, and marketed as, a reverse cycle air conditioner. Using an air conditioner in this way to produce heat is significantly more energy efficient than electric resistance heating. Some homeowners elect to have a heat pump system installed, which is simply a central air conditioner with heat pump functionality. The refrigeration cycle can be reversed in cold weather. When the heat pump is in heating mode, the indoor evaporator coil switches roles and becomes the condenser coil, producing heat. The outdoor condenser unit also switches roles to serve as the evaporator, and discharges cold air, colder than the ambient outdoor air. Heat pumps are more popular in milder winter climates where the temperature is frequently in the range of 40-55 DEGF, 4-13 DEGC, because heat pumps become inefficient in more extreme cold. This is due to the problem of ice forming on the outdoor unit's heat exchanger coil, which blocks airflow over the coil. To compensate for this, the heat pump system must temporarily switch back into the regular air conditioning mode to switch the outdoor evaporator coil back to being the condenser coil, so that it can heat up and defrost. A heat pump system will therefore have a form of electric resistance heating in the indoor air path that is activated only in this mode in order to compensate for the temporary indoor air cooling, which would otherwise be uncomfortable in the winter. The icing problem becomes much more severe with lower outdoor temperatures, so heat pumps are commonly installed in tandem with a more conventional form of heating, such as a natural gas or oil furnace, which is used instead of the heat pump during harsher winter temperatures. In this case, the heat pump is used efficiently during the milder temperatures, and the system is switched to the conventional heat source when the outdoor temperature is lower. It also works on the basis of Carnot cycle. Absorption heat pumps are actually a kind of air source heat pump, but they do not depend on electricity to power them. Instead, gas, solar power, or heated water is used as a main power source. Additionally, refrigerant is not used at all in the process. An absorption pump absorbs ammonia into water. Next, the water and ammonia mixture is depressurized to induce boiling, and the ammonia is boiled off, resulting in cooling. Some more expensive window air conditioning units have a true heat pump function. However, a window unit that has a heat selection is not necessarily a heat pump because some units use only electric resistance heat when heating is desired. A unit that has true heat pump functionality will be indicated its specifications by the term heat pump.
Refrigerants.
Modern refrigerants have been developed to be more environmentally safe than many of the early chlorofluorocarbon-based refrigerants used in the early and mid-20th century. These include as HCFCs, R22, used in most homes today, and HFCs, R134, used in most cars, have replaced most CFC use. HCFCs, in turn, are being phased out under the Montreal Protocol and replaced by hydrofluorocarbons, HFCs, such as R410A, which lack chlorine. Carbon dioxide, R744, is being rapidly adopted as a refrigerant in Europe and Japan. R744 is an effective refrigerant with a global warming potential of 1. It must use higher compression to produce an equivalent cooling effect. Historically, Freon, a trade name for a family of halal-can refrigerants manufactured by DuPont and other companies, refrigerants were commonly used in air conditioners due to their superior stability and safety properties. However, these chlorine-bearing refrigerants reach the upper atmosphere when they escape. Once the refrigerant reaches the stratosphere, UV radiation from the sun homolytically cleaves the chlorine-carbon bond, yielding a chlorine radical. These chlorine atoms catalyze the breakdown of ozone into diatomic oxygen, depleting the ozone layer that shields the Earth's surface from strong UV radiation. Each chlorine radical remains active as a catalyst unless it binds with another chlorine radical, forming a stable molecule and breaking the chain reaction. The use of CFC as a refrigerant was once common, being used in the refrigerants R11 and R12. In most countries the manufacture and use of CFCs has been banned or severely restricted due to concerns about ozone depletion. In light of these environmental concerns, beginning on November 14, 1994, the U.S. Environmental Protection Agency has restricted the sale, possession and use of refrigerant to only licensed technicians, per Rules 608 and 609 of the EPA Rules and Regulations.
Uses.
Air conditioning engineers broadly divide air conditioning applications into what they call comfort and process applications. Comfort applications aim to provide a building indoor environment that remains relatively constant despite changes in external weather conditions or in internal heat loads. Air conditioning makes deep-plan buildings feasible, for otherwise they would have to be built narrower or with light wells so that inner spaces received sufficient outdoor air via natural ventilation. Air conditioning also allows buildings to be taller, since wind speed increases significantly with altitude, making natural ventilation impractical for very tall buildings. Comfort applications are quite different for various building types and may be categorized as commercial buildings, which are built for commerce, including offices, malls, shopping centers, restaurants, etc., high-rise residential buildings, such as tall dormitories and apartment blocks, industrial spaces where thermal comfort of workers is desired, institutional buildings, which includes government buildings, hospitals, schools, etc., low-rise residential buildings, including single-family houses, duplexes, and small apartment buildings, sports stadiums. Recently, stadiums have been built with air conditioning, such as the University of Phoenix Stadium and in Qatar for the 2022 FIFA World Cup. The structural impact of an air conditioning unit will depend on the type and size of the unit. In addition to buildings, air conditioning can be used for many types of transportation, including motor cars, buses and other land vehicles, trains, ships, aircraft, and spacecraft. Process applications aim to provide a suitable environment for a process being carried out, regardless of internal heat and humidity loads and external weather conditions. It is the needs of the process that determine conditions, not human preference. Process applications include these: chemical and biological laboratories, clean rooms for the production of integrated circuits, pharmaceuticals, and the like, in which very high levels of air cleanliness and control of temperature and humidity are required for the success of the process. Environmental control of data centers, facilities for breeding laboratory animals. Since many animals normally reproduce only in spring, holding them in rooms in which conditions mirror those of spring all year can cause them to reproduce year-round. Food cooking and processing areas, hospital operating theaters, in which air is filtered to high levels to reduce infection risk and the humidity controlled to limit patient dehydration. Although temperatures are often in the comfort range, some specialist procedures, such as open heart surgery, require low temperatures, about 18 DEGC, 64 DEGF, and others, such as neonatal, relatively high temperatures, about 28 DEGC, 82 DEGF, industrial environments, mining, nuclear power facilities, physical testing facilities, plants and farm growing areas, textile manufacturing. In both comfort and process applications, the objective may be to not only control temperature, but also humidity, air quality, and air movement from space to space.
Domestic use.
Air conditioning is common in the U.S., with 88% of new single-family homes constructed in 2011 including air conditioning, ranging from 99% in the South to 62% in the West. In Europe, home air conditioning is generally less common. Southern European countries such as Greece have seen a wide proliferation of home air conditioning units in recent years. In another Southern European country, Malta, it is estimated that around 55% of households have an air conditioner installed. In India, AC sales have dropped by 40% due to higher costs and stricter energy efficiency regulations.
Health issues.
Air conditioning systems can promote the growth and spread of microorganisms, such as Legionella pneumophila, the infectious agent responsible for Legionnaire's disease, or thermophilic actinomycetes. However, this is only prevalent in poorly maintained water cooling towers. As long as the cooling tower is kept clean, usually by means of a chlorine treatment, these health hazards can be avoided. Conversely, air conditioning, including filtration, humidification, cooling and disinfection, can be used to provide a clean, safe, hypoallergenic atmosphere in hospital operating rooms and other environments where an appropriate atmosphere is critical to patient safety and well-being. Air conditioning can have a negative effect on skin, drying it out, and can also cause dehydration.
Environmental impact.
Prior to 1994, most automotive air conditioning systems used dichlorodiFluoromethane, R12, as a refrigerant. It was usually sold under the brand name Freon 12 and is a chlorofluorocarbon halomethane, CFC. The manufacture of R12 was banned in many countries in 1994 because of environmental concerns, in compliance with the Montreal Protocol. The R12 was replaced with R134, a refrigerant, which has a lower ozone depletion potential. Old R12 systems can be retrofitted to a R134 by a complete flush and filter dryer replacement to remove the mineral oil, which is not compatible with R134A. Most refrigerants used for air conditioning contribute to global warming, and many also deplete the ozone layer. R22, one of the most used refrigerants, has a global warming potential 1,500 times that of CO2. Although those gases can be recycled when AC units are disposed of, uncontrolled dumping and leaking can accidentally release those gases directly in the atmosphere. Production of the electricity used to operate air conditioners has an environmental impact as well, including the release of greenhouse gases.